Beth.
And I'm Beth.
Welcome to Physics with Beth and Beth.
Hello everyone and welcome back to Physics with Beth and Beth. I'm Beth and today we are going to be talking about the science of the universe. Now, to be fair, the science of the universe is kind of what we've been talking about all year long. That's sort of what physics is by definition. I like to tell my physics students that physics is the language of the universe and math is its alphabet. But today we're going to zero in a little bit and talk about the science of space as part of our preparation for the AP Physics 1 exam. Now, our reason for doing this is because space science kind of used to be its own distinct unit within the AP Physics 1 curriculum, but recently with some curriculum changes, they scooched things around and space science kind of ended up being chopped up into a bunch of tiny pieces and scattered across the whole year. So we thought it might be helpful, we as in my fellow Beth and I, for you guys to see all of those different pieces combined together in one coherent piece in order to prep for the upcoming exam. So let's start out with a little bit of equation review, talking about some of those equations that you guys are hopefully pretty familiar with by now. The first of which being something you guys worked a lot with during your Newton's Laws of Motion unit, which is Newton's universal law of gravitation, which tells us that the force of gravity between two objects is equal to the gravitational constant times my first object's mass times my second object's mass divided by r squared. Now, this is the way the equation looks on your AP Physics 1 equation sheet, but what does this r really stand for? It can be tempting to say whenever you're going really quickly, like in an exam, you're under a time limit, you're stressed, to sort of not think about the context of what you're doing and say this r is, for example, if I was talking about the force of gravity between Earth and the moon, say that this r is either the radius of the Earth or the radius of the moon. But it's not either of those. Instead, this r represents the distance between the center of mass of Earth and the center of mass of the moon. So it would really be this distance right here. So whenever I'm writing this on my own paper, I often like to do like a little subscript 1, 2 so that I don't forget that. But whatever notation works for you is just fine. Just remember, this is neither the distance between the surfaces, that's not it, nor is it the distance between the center of mass of one object and its edge. It's not its radius, it's not the moon's radius, it is instead the distance between the two center of masses of our two objects. Don't forget that. But now let's move on to the next equation that you guys will see on your equation sheet, which is that the potential energy due to gravity between two objects looks pretty similar to our force of gravity equation with two exceptions. The first being that we have a little negative out here at the front. Now, negative energy is kind of a weird concept because we're used to thinking like negative force is negative because negative is indicating a direction, right? But with energy, we don't have directions. Energy isn't a vector quantity, it's a scalar. So what does this negative mean? Well, this negative is a way of us showing that you lose energy whenever you get stuck to somewhere by gravity. So right now, gravity is holding me down to Earth's surface. If I wanted to escape and get to a place of zero potential energy, I would have to bring in energy from the outside. Like I would have to get rocket boots or something in order to shoot myself off into space. I don't plan on doing that anytime soon, but that's why this is negative, because in order to escape, in order to get out of this little potential energy trap that we're in, we need to bring in energy from the outside. As you go farther along in physics, you'll start talking about things like potential energy wells and all kinds of things like that, and you'll start to get pretty darn comfortable with the idea of negative energy. But for now, just know it's called this because we have to bring in energy from the outside in order to leave. So that is the potential energy due to gravity. The one other place where this is different from our equation for force is that this r in our denominator is not squared. And the reasoning for that is because of the units, the difference in units between force and energy. This equation is what we need to get units of newtons, and this equation is what we need to get units of joules. A fun little review for you guys, if you want something extra beyond what we're doing in these videos, might be to go get a piece of paper, look up the units for the gravitational constant, and figure out what the units of this overall equation are. Spoiler alert, for force, they're newtons, for potential energy, they're joules. All right, but those are our equations about gravity. let's go and start talking about things moving in circles, because in space it turns out we have a lot of things moving in circles. Things revolving around other things. We have satellites, we have velocities, we have all kinds of stuff. So whenever we have an object moving in a circle, we know that that means there has to be a force acting on it. There has to be some force that we call a center-seeking force pulling it in a circular path. We say that such an object has an acceleration and that its centripetal acceleration is equal to its tangential velocity squared over r. If this is our centripetal acceleration, the acceleration we have that's pointed inward for us to be moving in a circular path, we say that the force that's pulling us in that circular path, our centripetal force, is equal to our mass times our centripetal acceleration. So just m times v squared over r, where this v is our tangential velocity. And this r is the radius of our path. So if I have an object revolving in space, our r is the distance between the center of its path and the edge. This first equation is on your AP Physics 1 equation sheet. The second one is not. It's not too hard to derive, but seeing it a couple of times and getting familiar with it can save you a few precious seconds whenever you're working on those tricky free response problems. A couple of other things. Well, I'm talking here about tangential velocity, but what is that and how is it related to angular velocity? Well, thankfully, this one isn't too bad and it's on your equation sheet, which is just that I can calculate the tangential velocity of an object by multiplying my radius of my path times my angular velocity. So Vt is equal to r omega. Similarly, I can translate between my tangential or linear and angular acceleration by just multiplying my angular acceleration by r. So these two equations are very much analogous to one another. And thankfully they're not too gross. So that's how we calculate tangential velocity and acceleration. Now there's one last thing that I want to go over that isn't on your equation sheet, which is more of a definition than anything else. So this is one that you guys really need to pay attention to. I'm going to give it a little star. If I want to calculate the angular velocity of an object, well, velocity in general is distance divided by time, right? And angular velocity tells us how many angles or how much angular distance we've covered in how much time. So if I'm talking about my angular velocity, I can relate that to a period of an object by saying that this is 2 pi divided by t. Because 2 pi is the number of radians in a full circle, and t is the amount of time it takes me to complete a full cycle of motion. So my angular velocity is going to be equal to the number of radians I cover divided by how long it takes me to do that. So very much analogous to normal velocity there, but this equation isn't on your AP Physics 1 equation sheet, and sometimes when you're stressed and moving fast, it can be difficult to be like, oh gosh, how do I relate those two things? I can't remember. So practice with it a little bit before, which is what we're going to do in this video. So instead of going over equations now, because I think we've covered everything we need to, let's go into a couple of quick practice problems. So first, let's say, well, a little bit of background about me. I have a cat, and her name is Juniper, and she is, scientifically speaking, the most impressive cat in the universe. And so in this problem, let's talk about my very impressive cat, Juniper, traveling to the moon. So I want to find what the acceleration due to the moon's gravity is on Juniper. In other words, I'm looking for the little g of the moon. Now, I know that I can write the force due to gravity on an object as big G times m1 times m2, where m is the mass of my first object and m2 is the mass of my second object. So maybe something like mj for the mass of Juniper times mm for the mass of the moon, divided by rjm squared, or the distance between Juniper and the moon. And that's how I would represent the force due to gravity on Juniper. Well, I also know that that's if I have Juniper standing on the surface of the moon, well, the net force acting on Juniper is the force of gravity, right? So I know that I can write from Newton's second law the net force as mass times acceleration, where mass is Juniper's mass, not the moon's mass, because I'm talking about the net force acting on Juniper right now. So if this m is Juniper's mass, and this A is her acceleration, well, the acceleration due to gravity, oh, that's just little g. So this little g goes right here where my A is, because Juniper's acceleration is the acceleration due to gravity. Now, at this point, some of you might be thinking, oh no, this isn't good. First of all, why is your cat on the moon, Beth? That doesn't sound like a very good place for cats. Don't worry, Juniper's very talented and she has a spacesuit. But then, also, some of you might be thinking, well, wait, but I know, because I've gone through an entire year of AP Physics 1, that the acceleration due to gravity on an object is completely independent of its mass. If I have a really heavy cannonball and a much lighter cannonball, they should fall at the same rate, and I know that. So I don't like that I have this M here. That's bad. And you're right, it is bad. Thankfully, it cancels out, because I have an MJ over here and an MJ over here. So if I'm trying to solve for this G, to get it alone, all I have to do is divide both sides by Juniper's mass, which means this one cancels and this one cancels. And we're left with a little expression that G times the mass of the moon divided by RJM squared is equal to G. There we go. The one thing to note though is if Juniper is standing on the surface of the moon, then this R right here would just be equal to the radius of the moon. The distance between the center of Juniper's mass and the center of the moon's mass is just the radius of the moon. So I could just replace this with something like this and be good to go. And there you go. That's how you calculate the acceleration due to gravity on another body, whether that's the moon or a planet. And it doesn't matter. The same math works for not cats too. So even if the problem on your AP Physics exam isn't specifically asking about my cat Juniper, the same math still applies, thankfully. All right, so let's go on to the next problem. Let's say that instead of standing on the moon, Juniper has gone even farther off into space. She's a very adventurous cat, and she is now revolving around Jupiter. She's now rotating around Jupiter. So I've got Jupiter here, and I have Juniper in her little spacesuit rotating around the moon. This is my beautiful artwork. So let's say I wanted to find Juniper's tangential velocity as she rotated around Jupiter. How would I do that? Well, a good place to start is probably by thinking about the forces acting on her. We know that the net force acting on an object is equal to that object's mass times its acceleration, Newton's second law of motion. So, well, what are the net forces acting on Juniper? Well, we know that that's just going to be the force of gravity between Jupiter and Juniper, the Juniper force, in other words, Juniper force. So, I know that the net force acting on her will just be the force of gravity, which we just practiced quite a bit with. That's just G times m little j for the mass of Juniper times m big J for the mass of Jupiter, divided by r Jupiter squared is equal to the mass of Juniper times her acceleration. Okay, but what is her acceleration? Well, we know if we have an object that's going in a circular path, there needs to be some acceleration turning it in a circular path, right? And what is the magnitude of that acceleration? Well, first of all, this is centripetal acceleration because we say that it's pointed inward because it's what's causing her to rotate in a circle. And the magnitude of that acceleration, we talked about this at the start of our video, is always equal to v squared over r, where v is our tangential velocity. So I can take my little equation here and rewrite it squared is equal to mass of Juniper times v squared tangential over r. And there we go. Okay, so now we say, well, what was I trying to solve for? I was trying to solve for Juniper's tangential velocity, right? How fast she's zooming around as she goes around Jupiter. Well, now I have an expression that has velocity right here. All I have to do now is algebra to solve for it. We've done all the hard stuff with setting up equations. We can just scooch things around to solve for this v. So I'm going to do this a little quickly here. I'm just going to multiply both sides by r. That cancels out one of my factors of r in the denominator here. I'm going to divide both sides by Juniper's mass. That cancels this here. So that also cancels this factor of Juniper's mass in the numerator, which means that I'm now left with the acceleration of gravity times the mass of Jupiter divided by r is equal to v tangential squared. So if I want to solve for v, all I have to do is take the square root of both sides, and then I'm home free. So Juniper's tangential velocity is just equal to the square root of g times the mass of Jupiter divided by r. I really wanted to give myself a tongue twister with this problem. So there we go, that's how we would calculate tangential velocity. Now, but what if, instead of calculating tangential velocity, we were asked to calculate the period of Juniper's motion? How long it takes her to complete one full lap around Jupiter? Well, that's tricky because we don't have period anywhere here in this equation, right? But you might remember we can connect period to angular velocity because angular velocity is equal to 2 pi divided by period. Okay, well that doesn't help me much because angular velocity isn't anywhere on any of the math that I've written either. But maybe I can rewrite one of these things in terms of angular velocity. Here I have tangential velocity, and you might remember that converting between tangential and angular velocity is just a simple matter of multiplying by our radius. So now we have this little daisy chain of equations that we can now combine together. If I want to find my period, well, period is in my equation for angular velocity, so I can put that in right here. So I can rewrite tangential velocity as r times 2 pi over t. And then I know, well, I have vt right here. I'm going to erase all this and go back to this step right here. Let's undo all this. Okay, so if we're right back here, when we have g times our 2 m's divided by r squared is equal to m times v squared over r, well, I now know that I can rewrite v as this expression that has t in it. So the next step of our little daisy chain would be to take this guy and plug him in for v. So now I can take this whole expression that I have here and do mj, m big J divided by r squared is equal to m little j times r times 2 pi over t squared divided by r squared. A reminder that since this is v squared, everything that v is equal to also gets squared. It can be tempting to skip a step there, but all of this is being squared here. So now all we have to do is do a little bit of algebra in order to simplify this, because now we have t right here. It's hidden in the side of my equation, and I just hid it more so it's harder to see. There we go. So now we just need to solve for our period here, and we're home free. So I'm going to start by squaring everything inside here. I also am going to notice that I have, oh, this is just an r right there. There we go. Yeah, so I'm going to start by squaring everything here and then seeing if anything will simplify a little bit for me. So m little j and big J divided by r squared is equal to m little j times r squared times 2 pi squared divided by r times period squared. Okay, well, I have one factor of r in the denominator and 2 in the numerator, so that cancels out. I'm going to also divide both of my sides by the mass of Juniper here, m little j, because it's in my numerator on both sides, so I know that will cancel out as well. Okay, and now this is getting to look really gross, but we're almost there, I pinky promise. We have that the gravitational constant times the mass of Jupiter divided by r squared is equal to r times 2 pi squared divided by t squared. There we go. So I know I'm trying to solve for t, so I'm just going to multiply both sides by t squared in order to get him out from under the denominator. Just general algebra tip, if you're ever trying to solve for something that's trapped in the denominator on one side of your equation, your first step should always be to multiply it out of there to get it unstuck from the denominator. So I'm going to multiply both sides by t squared to free my little period from there. And I'm really running out of room, so we're going to erase this up here. So now we have t squared times g mj over r squared is equal to r times 2 pi squared over nothing, over 1. Now, I have t, and then I have all of this gross stuff that's being multiplied to it. Thankfully, all of this gross stuff is really just a fraction. What do we do in order to get rid of fractions? We multiply by their reciprocal. So I'm just going to multiply both sides of my equation by this guy turned upside down. So I've got t squared times gmj over r squared, and then I'm going to multiply by this upside down, so times r squared over g mj, so my g's cancel, my r's cancel, my mj's cancel, but if I do it to one side of my equation, I have to do it to my other. So this is r times 2 pi squared times r squared over gmj. And then if I go down to my next step, I will notice that all that I have left on this side is t squared. So to solve for t, all I have to do is take the square root of both sides. So t is just going to be equal to the square root of all of this junk, which simplifies whenever I combine it a little bit. I've got an r cubed, I have 2 pi squared, and then I divide that by g times mj. And there we go. And that, oh, this is the mass of Jupiter, not of Juniper. And that is how we calculate the period. So that was a lot of steps. It was a lot of algebra. But conceptually, what we did was really just a daisy chain of equations. So we said, okay, I know I can connect the net force that's acting on Juniper to her centripetal force, and I can connect that to her centripetal acceleration. I know that centripetal acceleration can be written as v squared over r. I know I can rewrite v in terms of my angular velocity, and I know that my angular velocity is related to my period. So I can rewrite my angular velocity in terms of my period, and then I can use that to rewrite my tangential velocity in terms of my period, which then I can use to rewrite my centripetal acceleration in terms of my period, which I can then use to rewrite my centripetal force in terms of my period. So it was a lot of steps, a lot of algebra, but in the end it was just remembering these two little equations and then plugging them into the same equation we used in the last problem. All right, that was a lot, but hey, space is pretty big, so there's a lot of science going on in space. Thank you so much for sticking with me through all of this. If you have any questions, comments, or concerns, please let us know in the comments, and we will do our best to get back to you. Thank you so much for sticking with me through all of this. Good luck on the upcoming exam, though I doubt you need it, and happy physicsing.